In the previous video, I introduced you the news vendor problem and talked about exciting applications. The video was rather long. I apologize for it. I could not find a natural way to break it. And this video is going to be still a little bit long, and we'll see. I also talked about the uncertainty and the need for forecasting future events. We talked about objective and subjective forecasting tools, and in this session, we'll keep continuing our focus on these objective forecasting models. I'm going to introduce a simple but a powerful tool called moving averages. I'm also going to mention a method called exponential smoothing. We're going to learn how to build on the descriptive statistics we talked about and how to adapt these statistics for prediction. We're focusing on descriptive statistics, and we're going to look at forecasting. With past historical data, moving averages, exponential smoothing in the advanced slide in another video. We'll do that in next video. Recall our past demand data. We had 100 periods and we observed data throughout them. Let me pull that up here. So this was our video in our data sets. There are 100 periods and each has a demand data here, and I plotted those and I put in the slides earlier. We observe data throughout them. In these 100 periods, let dt, let dt denote the demand observed in period t. Okay. From the past data, we have demands d1, d2, d3, and so on to d100. In this example, d1 is 29. Again, pull the Excel sheet here. d1 is 29. And d100 is 41. Now let's look into descriptive statistics, particularly the mean and the average, mean and the standard deviation. Let's start with the sample mean or sample average. Sample mean or the sample average is just the arithmetic average all over the data points, and you've seen this before. Suppose you have n data points, you sum up all n points, n demands, d1 through all dn, and divide the total number by the data points you have. That gives you the sample mean. We call it sample mean. What sample mean really does is, sample mean roughly tells you what to expect the next observation to be. And most of the time people call sample mean just mean. It is straightforward to calculate it, and it can also be calculated using Excel's average function, and you've done this before, right? Whatever an average is, the demand in the future will deviate from the average, and this is very important. Yeah, this is kind of conflicting. That was the meaning of the average. The meaning of the average is you expect the next observation to be the average or the mean, but more than likely, what you will see in the future is going to deviate, right, from that average. And that's why we need to talk about standard deviation. Standard deviation, as we saw before, is a measure of how much noise or variation from the average there is in your data. And the way to calculate the standard deviation is to look at the difference between the demand and the average, and you've seen this before. Square the differences and add all the differences for the entire data set. Add the squares of all the differences for the entire data set. Divide by n minus 1, where your data has n deviant points. Take the square root, that gives you the standard deviation. But however, standard deviation can be calculated using Excel, formula, STD-EV, and you've seen all other variants of it, which is simple and straightforward. Okay, let me show this to you in the Excel, and it's something you've seen before. All I did was to get the average. I would do average and 52.81, and to get the standard deviation I would do ST. You can just use the compatibility function or any other ones it really doesn't make a whole lot of difference. There's another point I really want to make. That's why I want to show this all over once again. About 13.73. Let me show this in a few smaller digits here. If I can figure this part out. Oh, it's there. Oh, in the wrong direction. All right, 13.73. All right. Now, this might be a good time to pause and look at how to calculate the descriptive statistics from our few weeks ago. Mean and standard deviations are two descriptor statistics of our data. If our data was normally distributed, it would be sufficient to describe the data, and that would be even for the predictive statistics. However, if we need to use our data to forecast, we need to adjust our sample standard deviation, right? We need to adjust our sample standard deviation for forecasting. We'll talk about the reasons a little bit more in a bit. Let's look at the notation for our forecast. This notation is usually not so obvious if you have not seen this before. Remember that we denoted past demands as D1, D2, D3, and up to DT, which are the past values of the demand. We're interested in making a forecast in period T for a future period. We have data up to period T. We did not we denote the forecast by letter F, and in this case we can use the letter F. We can see that the letter F has two subscripts, F, T, and T plus tau. Right? The first subscript tells you which period you are making the forecast in. The second subscript tells you which period you are making the forecast for. That means I'm making the forecast for period T plus tau in period T. Okay, let me say that again. For example, Ft, comma T plus tau means it's a forecast that's being made at period T for a period T plus tau, where tau can be 1 or 2 or 3. Tau denotes how many periods ahead you're looking. So Ft, comma T plus 3, as an example, is the forecast made in period T for 3 periods ahead. Let's put some numbers in there and look at an example. F 100, comma 100 plus 3 is the forecast made in period 100, right, for period 103. This is called a 3-step forecast. Why? Because we're looking to forecast 3 periods ahead. We're going to look at 1-step forecast for the most examples. This is because typically we are interested in the next outcome, or simply 1-step forecast. So Ft, comma T plus 1 is the forecast made in period T for the period T plus 1, right? So Ft, comma T plus 1 is the forecast made at T for period T plus 1. Just looking at another example, Ft minus 1, comma T is the forecast made at T minus 1 for the next period T. To simplify things, we'll use the shorthand Ft plus 1 is simply going to say that what is a 1-step forecast made for the period T plus 1. So if I want a 1-step forecast for period T plus 1, call it simply Ft plus 1. In other words, Ft plus 1 stands for Ft, comma T plus 1. Okay? Because we are assuming it's only 1-step forecast for the time being. Forecasting for the station, and again, we are assuming that we are forecasting for a stationary series. What that means is the future resembles the past. An example is our news vendor demand data. If you look at the news vendor demand data file, it shows no perceptible trend. So a stationary time series has the following form. Demand in any time period T, say demand dt, can be written as a sum of two things. Mu, which is a constant, right? Sum of two things. Mu, which is a constant, which is sometimes sample average, plus epsilon, which is a random variable. Epsilon t is a random variable with mean 0. See that the mean and the standard deviation are not dependent on time, and therefore there is no trend in this data. And it's a stationary time series. We say random variables we spend discussing about random variables quite a bit in the first couple of weeks, so it's a good time to revisit them if you need to brush up your knowledge on random variables. Let's move forward by thinking about how to use past data for forecasting. Two common methods of forecasting stationary series are moving averages and exponential smoothing. I'll cover moving averages in this video and exponential video in the next video. Exponential smoothing in the next video. Moving average method. In this moving average, the forecast is the arithmetic average of n most recent observation. Will denote the moving average method that uses n data points simply as MA in braces n to come up with one step ahead forecast for period t using moving average method. All we need to do is following. To come up with a forecast for period t, ft, right? We call it ft. You take the n data points from the past periods, going from t minus 1, t minus 2 up to t minus n, and then divide it by n. Right? The average of your past data points give you the forecast for your next period. So if you want forecast for several days ahead, that is, you wanted a multi-step forecast for moving average. The multi-step forecast is the same as the single-step forecast. So you can just use the single-step forecast as your multi-step forecast under moving averages. We saw how to come up with one-step forecast using moving average for a period t. You might wonder why it is called moving average method. Right? It is called slide here. Okay. It is called a moving average method because the chosen data points move and are always the most recent n data points. For example, if you wanted to forecast for period d minus 1, if you're at period d, you look at, for example, if you wanted to forecast for at period d, you look at n data points that went from d minus 1, d minus 2 up to d minus n. Now if you want to forecast for the next period, d plus 1, what happens is you have one fresh demand data, that is dt, and you can add that there and you'll drop the last observation. We saw that here. So at dt, is at time t, you're going to make a forecast. Right? So you're going to use dt minus 1, t minus 2, all the way through t minus n. You used n data points. You made a forecast. Now, at time t plus 1, right, you want to make a forecast for t plus 1. What you do is you drop this last data points, which is not here, and you added another data point which you just observed in the last period, dt. Right. So this is why we essentially moved the data. We are using one period, so we moved it by one period. We added dt and we took away dt minus n. Let's use an example to understand this better. Let's calculate the moving average for past 10 periods. Using our notation, we'll call this MA10. Okay? First, we'll look at the descriptive statistics, and then I'll show you how you change that descriptive statistics to use for forecasting. Okay? All right. Let's go to the Excel file here. And instead of using this demand data, let me use, I selected just some data points out of here. I call it one mat template. It's just the last 80 data points and the first, so that I don't have to keep scrolling down. All right, I want to get the moving average using, say, first let me do MA10. Okay, MA10. To do MA10, suppose I'm sitting here at 100th period. I want to use MA10 to predict what's going to happen at 101st period. Well, to get there, first I would need a an average using the last 10 points. For the last 10 data points, starting at first, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or I wait one more, I went 11 here. 10. Okay, you can see when you scroll, you see 10. All right, so I use 10 data points. My average is 49.6. All right, let me get the standard deviation using this. STD. Again, I'm going to use the last 10, and I got, let me make this a little smaller here. Oh, I keep doing that. All right, 10.28. All right, let me do just one more with say MA20. Now what I would do is I would calculate the average using last 20 data points, and similarly I would calculate the standard deviation using the last 20 data points, right? So now if I'm using a moving average of 10 periods, this will come handy. If I'm using moving average of 20, these numbers will come handy. Let me make this to step 2. The important thing is, the more data you have, the more ability you have to calculate these numbers and more confidence you have in the forecasting process. We can use this idea to these numbers we calculated for prediction or for forecasting. We call this predictive statistics. In operations, the mean of predictive statistics is same as the descriptive sample mean. In other words, the descriptive sample mean we calculated is the unbiased estimator of the mean of the true demand distribution. Hence, the sample mean that you calculated can be used for prediction. However, because of the insufficient data, the standard deviation of the prediction needs to be adjusted. And that's what we are going to do in the next step. And this concept of this insufficient data comes into picture because when we're doing moving average, we use smaller number of samples. Okay. All right. How do we go about doing this? The standard deviation for prediction is going to be the standard deviation we calculated plus a corrective factor. And the corrective factor is S, standard deviation calculated, divided by the square root of n, where n is the total number of data points you used. Let's look at some predictive statistics when we use 10 data points to get your moving average. When the data is normally distributed, the mean for prediction is the same as descriptive sample mean. So the mean was mu equals to 49.6, right? However, as we noticed, the standard deviation for prediction needs to be adjusted. And the adjustment gets you the sigma, what we are really after. So here we calculated S is equal to 10.28 plus 10.28 divided by square root of 10 because we used 10 data points. That's what gets us 13.53. As you can see, there is a significant correction. Now we can use this mu and this sigma for predictive purposes. Let's continue with this example for descriptive statistics using 20 data points or moving average of 20. Again, we calculate the sample mean. The calculated sample mean from the last 20 data points was 51.95. That's our descriptive sample mean. The sample standard deviation comes out to be 9.62. Let's do an example for predictive statistics using 20 data points. Again, When the data is normally distributed, the mean for the prediction that we got before is the descriptive sample mean is sufficient. The mean for prediction is same, 51.95 that we calculated. We expected that the demand in the next period is going to be 51.95 on average. However, the standard deviation for the prediction needs to be adjusted from what we calculated on the descriptive statistics. So the standard deviation for prediction is going to be sigma, which equals to this S, 9.62, plus 9.62 divided by square root of 20, which comes out to be 11.77. For forecasting purposes, we can assume that the actual demand distribution will deviate from the average with the above standard deviation, which is 11.77. Now let's think about using more data. As we have more data for forecasting, what happens is descriptive statistic approaches predictive statistics. As we have more data, we gain more confidence for our prediction. Also note, as the number of data points increases, the descriptive standard deviation approaches the standard deviation of prediction. That is, as n becomes larger and larger, the second term, the correction term, disappears and the sigma becomes almost equal to S. Suppose we are using all the available data of n equals to 100. The descriptive statistics as calculated from Excel are as following. Mu is 52.81, S is 13.73. If our data was normally distributed for normal distribution, the predictive statistics are as follows. The mean, mu, is still going to be the same, 52.81. However, the standard deviation for the prediction, as we saw before, needs to be corrected and adjusted. And that's going to be 13.73 plus a correction factor of 13.73 divided by a square root of 100, making it 15.10. So what does this really mean? That means for our demand for prediction purposes, we can use a normal distribution with a mean of 52.81 and a standard deviation of 15.10 in the coming weeks. And I'll work with you in an Excel video and how this comes into play with what we have learned before.